So here we have three long wires. I1, I2, and I3. We have an equilateral triangle, so that means that all the lengths on each side are the same, and the angles are 60 degrees each. So we'll solve part A first. We're being asked what's the magnetic field on I3 because of I1 and I2, knowing that each of these wires has its own current. The first thing I'll do is I'll draw each of the magnetic fields on this wire directly. The very first thing I'll do is I'll draw a straight line, and I'll exaggerate it a bit. Then I'll start with I1. I'll draw a circle around I1. And now we're going to use the right hand rule to help us find the magnetic field by I1 on I3. Assuming that you're watching this on your tablet, and your tablet is flat on the table, your thumb is going to point up towards the roof, and you're going to start curling your hands into a fist. As you do that, the magnetic field will point in this direction. It will point counterclockwise until you complete curling your hand into a fist. Now that you've done this, what you can do is make the circle larger so that it sort of overlaps with I3. And you see that at this point here, the magnetic field is sort of pointed this way. And that's what you need to keep in mind. The magnetic field is pointed this way. Because of I1. Now I'll do the same thing with I2. I'll draw a circle around it. This time the current is pointing, assuming that you're watching this on your tablet, and your tablet is flat on the table in front of you. Your current is going to point into the table, such that, so basically, to use the right hand rule, your thumb is pointing into the table, and you start to curl your fingers into a fist. As you do that, your fingers are moving clockwise. They're following a clock, how a clock moves. So this is like the general direction of the magnetic field because of wire 2. Now when I make the circle much larger, I realize that when the circle touches I3, the magnetic field is sort of pointed this way. Downwards. first thing to do in these types of problems is to always start with drawing the actual vectors out. Now the second thing we'll do is to actually find this angle here and this angle here. In order to do that, I will start with I1 again. I'll start by drawing a line this way. I'll try to keep it as straight as possible. Now this line represents the distance r, at least from here to here, right? The distance between the two wires. The magnetic field of this wire will always be perpendicular to the actual distance, to the r. So what I'm trying to do is the following. The angle here from this guy to this guy is 90 degrees. That's like certain because of the Biot-Savart law. I'll show you the formula sheet I have. Basically, you're actually taking a cross product here on this formula. So hence, that's why we have that angle of 90. So that's awesome. We know that this angle, it's inside that triangle. This entire angle here actually is 60 degrees. When we cut through half of this equilateral triangle, we'll split it into two 30-degree angles. So this one up here is 30, this one up here is 30. This angle here is not 30. You have to keep that in mind. How do we find this angle theta? It's very easy now. We use the triangle, so this is 30 degrees. That's awesome. That angle is 90. Now you realize that this is half a circle, right? And we've basically found that part of the circle, the angle that it makes, which is going to be 90 degrees plus 30, which is 120. So we do like half a circle, 180 degrees minus the 120. Because 90 plus 30 is 120, and you get 60 degrees. So basically, this angle here is actually 60 degrees. So really, like, the most important thing for this type of problem is this finding out the angles, because the angles aren't exactly the same. That's pretty much it. Other than that, it's the usual solving for Biot-Savart law. So basically, once you have the angles, you're pretty much good to go. Now, I'll try to find the angle for the second magnetic field down here. But first, I'm going to erase a few things because it gets far too messy. So again, I'll do the same thing. I'll start with I2, sorry. And I'm going to draw like that radius. I'll draw a line. Ideally to So yeah, anyhow, I drew this line. The radius between I3 and I2 is the following. Okay, from here till here. Now, I need to find this angle here. We already know that the angle between the radius and the magnetic field of this wire is 90. So this is 90 degrees. Again, like we've done here in this line, we've sort of chopped the equilateral triangle into two pieces. This angle was initially 60 and it got broken down into two 30-degree angles. So this angle is 30 degrees. So now we kind of do the same thing. We have half a circle. We do 90 plus 30, which is 120 degrees. And we do 180 minus 120. Which gives me 60 degrees. So this angle over here is also equal to 60 degrees. Now let me erase. So again, the most important part of this problem is just to figure out the angles. Once you have that down, you're pretty much chill to go with finding the components. The next step we're going to do is we're going to find the magnitudes first of each of these vectors, and then we'll sort of use sine and cos to find the actual components. So we have the following law. For a wire that is limited, for a wire that isn't infinite. Now, in this question, when we mentioned that we have three long wires, anytime we see the word long, we always assume that the wires are infinitely long, okay? Unless the question says, oh, the wire is 5 meters long, we always assume that it's infinite, unless otherwise indicated. So this is the formula for all kinds of wires, whether the wire is infinite or limited in length, like 5 meters or whatever. This formula applies to everything, both short wires and infinitely long wires. Now we have infinitely long wires, so let me draw an infinitely long wire. I'll draw arrows here to show that it's going to infinity. I'll draw a dot here. Let's say that I wanted to find the magnetic field at this point. This is the shortest distance between the point and the wire. I'll call it R. Now the angles here are theta 1 and theta 2, as we see up here in the equation. And that's just the point where I'm trying to find the magnetic field, the point in blue. When the wire is infinitely long, these two angles are actually 90 degrees. So when we take the sine of 90 degrees, we get 1. So we do 1 plus 1, which gives us 2. And when we do 2 divided by 4, because there's a 4 down here, we get half. So the actual formula we're getting for infinitely long wires is the following. Mu naught I over 2 pi r. So this is the formula we'll use to find the magnitudes first of each of the magnetic fields. I'll start with finding the magnitude of the magnetic field of the first wire. So this guy here. So here we have 4 pi times 10 to the power minus 7 Tesla meters per ampere times I1, which was 2 amperes, divided by 2 pi r. R is the length L, the distance between this guy and this guy. So it's 45 centimeters, and I'll convert it to meters, so that's 0.45 meters. So I'll do the same thing with the other wire. I'll find its magnitude. I'll first write down the equations, because this is ideally, let's say you were solving a test right now. You want to get all your work down first before actually calculating everything. Especially if you have a teacher who wants you to show all your work. The current for I2 was 10 amperes. And then the radius is the same as before, it's 0.45 meters. The distance between this wire and this wire. And now I'll plug these into the calculator. You get a value of 8.89 times 10 to the negative 7 Tesla as the magnitude of the first wire. As for the second one, we get 4.44 times 10 to the negative 6 Tesla for the second wire. Now I'll erase a few things. Now I'll find the actual components of the magnetic field of the first wire. So we kind of know that the magnetic fields are in the y-x plane. So they have an x component, an I component, as in an I component, and a y component, as in a j component. So this would be our x component, and that will be our y component for the first magnetic field. Now to find the I component, I do adjacent over hypotenuse. So that's going to be ka, so kato, adjacent over hypotenuse. So cosine theta b1 cosine of 60 I hat, and it's positive I hat because the magnetic field, the x component is pointed in the positive x direction, and same thing with the y component, it's also pointed in the positive y direction, and that's going to be opposite over hypotenuse. So that's going to be sine b1 sine of 60, where the b1 is simply this value we found, the actual magnitude of the magnetic field. And I would do the same thing for b2. In the case of b2, our y component is negative, and our x component is still positive. So we do the following. And minus, we put a minus sign for the y component. Why? Because again, I told you it's pointed downwards in the negative j hat direction. So we do b2 sine of 60. Again, the angle for the second magnetic field is also 60. Now it's simply a matter of plugging things in. So I found b1 to be so that's b1, and for b2 I got the following. Now I found the x and y components of each of the magnetic fields on the third wire. Now, there's one thing you're probably wondering about. What about the third wire? Well, the third wire does have a magnetic field all over the place except for right on top of it. There's no magnetic field from the third wire when you're standing right on top of it. That's because your radius, like the distance of this wire from itself is 0. The radius is 0. So what I'm trying to say is, when we look at this equation for I3, we're trying to find the magnetic field of I3, this radius, this distance of the third wire from itself is 0. So what happens is your actual magnetic field would be 0. So the magnetic field from the third wire is 0 on the third wire, that is, when you're standing on top of the third wire. So that's why we don't consider it. We only care about the magnetic field of these two wires, because they're actually some distance apart from the third wire. Hence, they actually have a magnetic field around them that can affect the third wire. So now it's very simple for part A. We just kind of add them up. We add up each component with itself. So I hat with I hat and j hat with j hat. I'll do that in my calculator, and then I'll write the answer. Now again, kind of, notice how I'm writing the same exponent over and over again. In a test, you can just make things easier for yourself. You can factor it out of the I and j components. So before I get the net magnetic field, what I'm trying to say is you can just write B1 like this: 4.45 I hat plus 7.70 j hat, and then you put brackets and then you say times 10 to the negative 7. So you just factored out the 10 to the negative 7 instead of having to write it twice. Yeah. Now I'll find the net magnetic field. I'll plug it into my calculator. So we get 2.67 when I round it up a bit times 10 to the negative 6 I hat. So that's good. We got the right answer there. That's not an issue. And then no problem. And then for the j hat components, we get negative 3.08 times 10 to the negative 6. So there we go. We found the net magnetic field because of wire 1 and 2. I'll continue part B in a separate video.